Hi Chandra.
Hi, Bobby.
So last class we discussed about capacitive sensors,
Yes.
and I was mentioning that, suppose if you have these two electrodes, and let's say this is at Vs. By the way, this MU stands for measurement unit.
Okay.
Let's say this is at some Vs sinusoidal signal, let's say, and this is at ground.
Okay.
And then we said, if we bring in a conductive sheet like this and then connect it to ground, this is what it will happen for the electric field lines.
Correct.
In the sense, these field lines will come from the top electrode, but goes to ground through this element.
Yes.
That displacement current will flow that way.
Yeah.
But then I have a different question. Suppose this ground connection is missing, what will happen?
I think it will be the same.
Is it? Because now if you look,
so it's floating.
This guy is floating.
Yes.
So that means it can take any voltage, whichever
yes,
you give.
Okay, so then it might not be the same.
Yeah.
Yes.
Yeah. Or the question is, if you have, let's say, voltages at, let's say all these points have same voltage, and then if I short a wire, using a wire, will there be any current flow? No.
No.
Because the same potential.
Yes.
So when you have an equipotential plane and then you introduce a plate there, a conductive sheet there, it's not going to make any difference.
No.
So the field lines will continue to be in this way, and hence there will not be, unless otherwise this guy is so thick and change the geometry there.
Yes, then it will.
Yeah.
Yes.
What we are talking is a thin sheet.
Right.
So it's important that we ground this. So then you get this effect of shielding.
Correct.
Somehow we are not very particular about this aspect.
Right.
So I thought I will just mention. We were also mentioning, if you bring in this differential configuration, push-pull configuration, then there are some benefits.
Right.
Something which is common to both capacitors C1 and C2 will get cancelled if you do a ratiometric operation and so on. We have seen one example like that. So in this case, suppose if this is the case where you have two electrodes that are fixed and then you have another electrode which is moving in, that changes the current IC.
Yes.
Then how do you bring in differential arrangement?
Differential arrangement means?
So differential means I would like to get, let's say, one capacitance C1 that goes up, let's say, and then I would like to have another capacitor C2 that comes down in a push-pull arrangement.
Right.
So, we had a displacement sensor like this, where two capacitors were there, and we had three connecting nodes. So when this, let's say C1 increases, we used to get the C2 decreasing.
Yes.
So it changed in a push-pull manner.
Right.
And then we have shown that if you do this C1 minus C2 by C1 plus C2, we were talking about one C naught, a nominal value of capacitance, which may change, if the distance between the arrangement change, etc. In the previous displacement sensor case.
Yeah.
So this output we showed that this is equal to plus or minus kx in the previous discussion. So we would like to get that kind of arrangement.
Okay.
So here, of course, we have seen that even if this goes up and down by a little bit, it will not make a difference in the current IC. So we are happy about it. But how do you get a differential arrangement? So probably we will need one more of this set, and when this electrode goes in, it has to be coming out from somewhere.
From the other side, yes.
So it could be something like this.
Okay.
Right. Where we have, let's say this yellow guy is a moving element.
Right.
And then you have two of this.
Yes.
So if I move this direction, C1 will decrease, C2 will increase, and vice versa.
Correct.
Of course, I need to have a ground connection.
Yes.
Otherwise, we will be just moving there
Nothing
without
will
changing
happen.
capacitance.
So this can be used as a displacement sensor?
This can be used as a displacement sensor. Now, depending on the configuration, electrode configuration you have, let's say you have an arrangement like this,
Okay.
where I have a top electrode in a circular manner,
Mm-hmm.
and the bottom electrode is also in that way.
Okay.
Let's say the top and bottom are connected, like this.
Okay.
I'm showing only one set. Let's say the moving electrode, which is connected to ground, when it comes out, or in this case it is already in. So if I measure the capacitance between the top and the bottom, it will be minimum now,
Yes.
provided the moving plate is at ground.
Mm-hmm.
Now, if there is an angular displacement and if the moving plate comes out, then the capacitance between top and bottom will increase
Yes.
gradually.
Yes.
So this is what we were trying to mention in the last class, but
Right.
I was making a drawing which was not very clear.
But this is only a
Small angle.
small angle, but then if you want to push-pull, you'll need something else on the other side.
Yes.
Correct?
Yes. So that is where, sorry, we have used a half circular plate and then 4 sets of quadrature shaped plate. I have a better drawing here.
Yes, yes, something like this.
Yeah,
Correct.
this is an exploded view
Right.
in this direction. I mean, actually this is a very compact device. So if you look here, you have a top plate,
Mm-hmm.
which is made of 4 quadrature shaped electrodes,
Okay.
and then there is a corresponding bottom layer.
Okay.
Bottom layer and top layer, they are identical.
Okay.
And then there is a middle layer,
Mm-hmm.
which is a half circular shaped plate.
Okay.
So this half circular shaped plate is connected to the spindle
Mm-hmm.
mechanically.
And what's this green?
So the green one
Let's
is
see.
just an insulator.
Between the plates.
Yeah, because it's compact. I mean, when you collapse this,
Yes.
they need not touch each
Touch
other.
each other.
Capacitance should form, so you need an insulator.
Right.
So it's a very thin layer of insulator. I think we have used a mylar sheet.
Mm-hmm.
So it's a very thin layer of insulator. So that way now, if you look, you have, let's say, this TP1 and BP1. That forms a capacitance C1.
Yes.
Similarly, TP2 and BP2 form C2, C3 and C4 and so on.
Mm-hmm.
So each set forms a capacitance. Now, depending on the position of this middle plate, this capacitance will vary if this middle plate or if this spindle is grounded.
Yes.
So I am just referring to this case where, let's say, this guy is grounded, and then if you are coming out, this capacitance increases. No?
Right.
What we measure across this.
So that half circle then is grounded.
Yes, half circle is grounded
Yes.
through the spindle.
Spindle.
And what we are trying to measure is the rotation of the angular movement of the spindle, which is actually connected to the measure and to which, where we are interested in the angle.
So then the voltage, where is that connected?
Yeah. So now the rotating part here is only the half circular plate.
Yes.
Everything else is fixed.
Okay.
So you can make connections from these electrodes.
Okay. Okay.
Correct.
Right.
The top and bottom electrodes are
Yes.
fixed
Correct.
on a material,
Yes.
a sheet. So we can have electrical connections from there.
Okay.
Right? So that I can measure C1, C2, C3, C4,
And that is also connected to a common ground.
which is connected to,
So the spindle is connected to ground,
yes.
and that voltage, you're giving a voltage to that.
Yeah. So that depends on how you measure.
Right.
So if you are using, let's say, like we discussed last time, if it's a part of a integrator or something, let's say you are sending some current and then looking at the output voltage.
Right.
Then we would choose, the bottom electrode at the ground potential or virtual ground,
Yes.
and the top electrode will be the
Voltage.
op-amp's output.
Right.
Okay. So there are different ways to measure. We will not go into that detail.
Right.
But as long as, let's say, there is a measurement unit available to measure this capacitance, and in that measurement unit, if the bottom electrode is at ground potential or virtual ground potential, then this method can be utilized to get a variation or change in capacitance as a function of the angle.
Yeah.
So this is a situation where, let's say, angle theta is 0. I am just showing the bottom electrodes and the half circular shaped electrode alone. So in this condition, as you can see, this these two electrodes, these two sets, BP1 and TP1, BP2 sessions are covered by the grounded moving electrode.
Yes.
So that means the capacitance C1 and C2 will be at the lowest point, and these areas are open, means BP3 and TP3, BP4 and TP4, there is nothing in between. So there is a capacitance, two capacitor values available.
Right.
So they both will be at high value, the maximum value, the other two will be at the minimum value.
Correct.
Now, if you start rotating, let's say like this. So as you can see, these areas are getting relieved from the presence of the grounded moving electrode. So that means capacitance between BP1 and TP1, which is C1, will start increasing as a function of theta.
Yes.
Now, at the same time, this guy is entering into this BP3, and the electric field lines in these areas will be getting shielded. So effectively, the capacitance between BP3 and TP3, which is C3, will be decreasing. So as you pointed out, you have C1, which is increasing, C3, which is decreasing now. So you have a push-pull pair now. On the other hand, here nothing is happening, although it is moving.
Shielded.
Yeah, it is still shielded.
Yes.
Until this reaches, theta reaches 90 degree.
Right.
And this area is just open. There is no moving electrode there, so that capacitance is still maximum. Now you can think about other, as you move 360 degree, how this capacitance vary. The same logic can be extended, and then if you plot those capacitance values. We have briefly discussed about C1, for the 90 degrees, C1 we said it will be keep increasing like this.
Yes.
And C3 we said it will be decreasing like this.
Correct.
The C2 will be at minimum, C4 will be at maximum. That's what we discussed.
Yes.
So now this logic can be extended. You will see that these capacitance values vary in this fashion.
So this also means every 90 degrees, this will be repeated, but it will be like a mirror, the opposite way.
Yeah. So see, first 90 degree, the C1 increased.
Yes.
By the time the moving plate moved out of BP1, TP1 area. And so that means
it will be like
this is somewhere here.
Yes.
So further angles for another 90 degree, there is no change here.
Correct.
That's what you see the maximum value there.
Yes, but then from there, if you do go the other way, like if you have a mirror,
yeah,
it will kind of repeat, but in the opposite direction.
Yeah, so we can just follow.
Yeah.
So let's say it moved up to this.
Yes.
Till that there is no effect.
Yeah, so that effect and the initial effect should be the
Yeah,
same.
yeah.
Right.
So let's see whether it comes like that.
Right.
Now if I rotate further, that means you are entering into this.
Correct.
So that means C1 will start reducing.
Yes.
So that's what you see, the C1 start reducing.
Right.
And once it reaches this much, you have covered fully.
Yes.
So you reach this minimum value, and so on.
Yes.
Right.
Correct. And then that's where CM, yes.
Yeah. So
C3 and C4, then maximum. Right?
yeah.
Yes.
So maybe students can just think about this logic and draw by themselves and see whether this plot comes.
Right.
Right? Because the logic is the same. I don't want to go through the same. So what you see is you have a push-pull pair here for 0 to 90. Then this push-pull pair repeats again repeats for this area.
Exactly. That's what I was.
Yeah. So during this time, the other two pair are in sleep mode. I mean, they are not changing.
Yes.
As you can see here. Right. Now for the other two quadrants, you can see 90 to 180, C2 and C4, they change in a push-pull manner.
Yes. The other ones are sleeping.
Other one is sleeping. And then 270 to 360, again there is a push-pull change for the C2, C4 pair.
Correct.
So actually you are getting two pairs of differential capacitors.
Yes.
One is C1 and C3, other one is C2 and C4. They work in certain quadrants.
Yes.
As you see here.
Yes.
So now the question is, if you have this piecewise linear sections, can I get a straight line output like this? Because if I am buying an angle sensor, I would like to get with this angle, okay, this is my output, this is the angle, this is the output.
So output with respect to angle.
Angle. Should be something like this.
Right.
So can I achieve that from these pieces? That's the question.
Well, it repeats. So
yeah,
sure.
it smells like there is a possibility,
yes, yes.
but how do you do that? There may be various ways to do. So one of the ways is, maybe students can also think how to get this. One of the ways is, so let's say we do a ratiometric calculation for C1 and C3. Let's say C1 minus C3 by C1 plus C3. How it will look like, we can just check it. So what I get is something like this.
What is this one? C1 minus C3.
C3 by C1 plus C3.
C3,
so it's a ratiometric calculation which you have done earlier for the other measurements.
Right.
I'm just checking whether what it gives.
Right.
So as we expected, it's giving a linear change for 0 to 90 and then 180 to 270. Now, we know the other pair is active when this pair is not active.
Yes.
So, we see, I mean, if you do C2 minus C4 by C2 plus C4, you see that this is linearly changing this portion and here.
Yes.
So, when you do this calculation, actually, because you are doing this ratiometric operation, it changes from 1 to minus 1.
Yes.
So now, suppose if I add these two, I mean, I have this one signal and I have this another signal, right. So one is changing from 0 to 90 and 180 to 270, the other one is changing in the other segments.
Right.
So if I add these two, it may be better.
Right.
So if I just add, we will get a signal like this, right. Maybe don't look at the y-axis, because this is changing linearly for this portion. After that, this is changing. So when you add these two, it will be a straight line for that portion.
Yes, but at some stage it will cancel. Right? Will it?
It may not cancel, but after that, you see this is decreasing. Then the output starts decreasing here.
Okay, yeah.
And then the other one starts decreasing, so output starts decreasing.
And then that stays constant. So
yeah.
That's why it's decreasing.
Yeah.
Yes.
Yeah. So if you plot that, you will get a piece like this.
So you have linearity until 180 degrees.
180 degree. Yes. And then actually it replaces, I mean, like the magnetoresistance effect that we discussed, there is some problem here. This and this I cannot distinguish.
Yes.
So somehow I need to make this like this.
Correct.
This has to come here.
Yes.
Right. So, suppose if I can multiply this signal with 1 for this duration and then minus 1 for the rest of the duration, then this is possible.
Yes, because then you'll move it up.
Yes, yes. I mean, to enable that, I have done a minus 2. So that this,
You have done what, sorry?
I mean, this sum of these two, when you do that, the whole signal will not be below 0.
Okay, I see. You're right. Yeah.
So, just to make that below 0, I have subtracted 2.
Okay, yeah, fair.
So that we can apply this logic of 1 and minus 1.
So, it's like an offset.
Yeah. Now, how do you get 1 and minus 1? I mean, we need to somehow know this is positive for this person. So, the same ratiometric operation, if you subtract these two signals, I mean, I have this and I have this. If you do the difference of this and then just look at the sign of it.
Then you get.
Yeah. So, what we see is it is plus 1 for this region and minus 1 for this region.
Okay.
So, you just have to multiply these two. The sum of these two minus 2 multiplied by sine of this.
Then you get plus 1 or minus 1.
Then you get this.
Very nice.
So, this is one way to get a linear output, for full 360 degree. Now, the ratiometric computation, I mean, there are circuits to realize this ratiometric operation straight away and get the output.
Okay.
Either analog or digital domain you can get. So, once you have, let's say, in digital domain, we just have to take sum of these two, subtract 2, and then look at the difference of that and look at the sign of it.
Right.
Multiply these two. That's all. It's not a complicated calculation that you need to realize.
Right.
It's a very straightforward.
But then you use some circuitry to do this.
Yes.
Automatically.
We use a circuitry to do this or to get this ratiometric output for both cases. So, you have this two output. If you have a summing amplifier, I can just add this 2 and a difference amplifier minus 2.
Right.
I may also have to look at ways to find a difference and then get sign of it and maybe a switching arrangement to have a flip for the 180 to 360 degree.
Right.
Let's leave the how to realize this, because that may be slightly beyond this scope of this. But if students are interested, they can definitely look at it. There are circuits available to do this. So this is another application.
Right.
We have talked about linear and angular displacement measurements.
But using capacitive effects.
Using capacitive. Because one thing is I mean, of course, we know this guy doesn't consume much power.
No.
Correct?
Correct.
Because I mean, if it's a sinusoidal excitation, if it's an ideal capacitor, there is no power loss there.
Right.
Or it will be very low compared to a resistive sensor or even inductive sensor, etc. Even inductive sensor, there is some resistance. There will be sometimes magnetic core, there will be losses there. Compared to all that, this gives a very low power sensor.
Right.
And look at the fabrication challenges. I mean, there is nothing. It's just a plate. You are shown this interdigital structure. It's easy to make.
Yes.
In this case, it's just couple of electrodes. Can be copper or aluminum or things like that. Easy to fabricate.
Yeah, you just have a circle and just cut it.
Yes. So construction wise, manufacturing wise, is very easy. So obviously that way the cost of the sensor will also be low.
Right.
So some challenge here is, I mean, we have discussed about the fringing field and so on. How do you get rid of or reduce the effect of it? In fact, here you can see that I have introduced an annular ring here, which is actually connected to ground.
Okay, so it's like a guard ring.
Yeah, it's like a guard ring. Because we have discussed in the previous case, the central, the moving electrode here is at ground.
Yes.
So I kept the annular ring at ground. So
So there'll be no field
Yes.
going out.
So there will be no fringing at the
Yes.
periphery.
Right.
Fringing will be there, but this system will not be affected.
Right.
So those are certain cases. I mean, things we'll have to look at, and some amount of complexity is there in the capacitance measurement circuits. But these days, electronics are, I mean, easily available. There are several schemes available depending on the update rate you want, depending on the resolution that you want, and so on. There are various circuits available. There are also commercially available ICs available to measure capacitance. In fact, if students look for capacitance to digital converters, CDCs, I mean, with maybe the knowledge from the analog courses that they have, certain configurations could be realizable easily. Also, there are CDCs available in the market with even 24-bit resolution and so on.
Oh, wow. Very good.
Yeah, and not so very expensive. Even those are not very power consuming units. So overall power consumption that you can achieve in this capacitive based sensing is very low compared to most of the other schemes.
Right. So you're saying even if you give, let's say, an AC waveform as your voltage,
Yeah.
you can still use this capacitance to digital.
So this capacitance to digital converters, there are various schemes. Some use as AC excitation, but most of them use just a square wave.
A square wave.
Yeah. So it may be slightly beyond this course, but there are sigma delta based capacitance to digital converters. There are also, let's say, dual slope capacitance to digital converter, and so on.
Right.
So most of the analog to digital converters which are available, some of them are modified to accommodate this capacitors or the sensing capacitor in as a part of the circuit itself.
Right.
And then that gives an output corresponding to the value of capacitance.
Right.
So that's why they are called as CDC, capacitance to digital converter.
Digital. Right.
The other one was ADC, analog to digital
Yeah.
converter.
That's just normal any analog
Yes.
waveform, right?
Yes. Yes.